So hello everyone and welcome back to the good stuff we have been doing. Today in this video we have before us a formidable sum involving polylogarithms, and polylogarithms have been defined and featured on this channel, and they are very useful functions because they are useful especially if you deal with logarithmic integrals featuring logarithms. You will see a lot of polylogarithms. And what are they? Well, for review, you can define them: the polylogarithm of order n of x as to be the sum as say k runs from 1 to infinity. Then you have an x to the k power, and then you have a k to the m power. And for example now, if you take n equals to 2, you have the dilogarithm which is of x, which is defined to be the sum as k runs from 1 to infinity of x to the k divided by k to the second power. And of course, especially you can see that the logarithm of 1 is pi squared over 6, which is zeta of 2, which is obviously the sum as n runs from 1 to infinity of 1 over n to the second power. This happens when we take x equals to 1. And surprisingly, polylogarithms are convergent when x is strictly is less than or equal to 1. So this is where they are defined. For example, there is no sense in writing the dilogarithm of 2, okay, but there's a sense in writing the dilogarithm of 1 over 2. And likewise, we define the trilogarithm also in similar fashion. The trilogarithm of x is the sum as k runs from 1 to infinity of x to the k all divided by k to the third power. So now this polylogarithm of order 7 is going to be written as follows: the sum as k runs from 1 to infinity of x to the k power, then you have a k to the 7 power. So you see that this our sum here is the sum of a sum itself. So basically, for order 7, if the argument is e to the negative 2 pi n, then you would have to write this as the sum as k runs from 1 to infinity of say e to the negative 2 pi kn all divided by k to the 7th power. So you see that we have all of this is equal to this here. So we have a double sum to work with, and it may look scary, but of course that is what this channel is for. This channel is for all those problems that people are even afraid to look at. That is the kind of problems we solve here. Of course, that does not mean that we want to solve the most complicated problems only. Even simple problems are still featured on this channel, but my own is to show people and everyone the beauty of mathematics, and sometimes beauty lies in complexity. So let's proceed. Let's start with a double sum s. So our double sum s is equal to the sum. So our sum is equal to the sum as n runs from 1 up until infinity of what? The polylogarithm of order 7 of e to the negative 2 pi n. And we say that this is equal to the sum as n runs from 1 to infinity of the sum as k runs from 1 to infinity of what? E to the negative 2 pi kn all divided by k to the 7th power. So now we have a double sum to play with, and it should not be too hard for us to wrap our hands around. Okay, let me rule a line here. We're needing this space. So to proceed now, what we need to do is that the sum start from n, but we can start from k first. Okay, so we have the sum as k runs from 1 up until infinity of 1 over k to the 7th power. Then we can now deal with the sum as n runs from 1 to infinity of e to the negative 2 pi kn. So this is a geometric series, obviously. So it has the sum as k runs from 1 to infinity of 1 over k to the 7. Then we'll have to write e to the negative 2 pi k all divided by 1 minus e to the negative 2 pi k. Yeah, so that is that. So it has this form, and the reason for this is simple, because we know that 1 divided by 1 minus x is going to obviously be the sum as n runs from 0 to infinity of x to the k power. So obviously if you multiply by x and you start the sum from 1, you will obtain this form we write here. So this is basically an elementary geometric series we are dealing with here now. But for the bottom, since you have a similar term, this is now going to be somehow, it looks like something you can maybe simplify, but it's not easy to simplify, because even if you attempt to multiply the top and bottom by, let's say, the numerator, you will have something like 1 divided by e to the negative. At this point, you have e to the 2 pi k, and then on this spot, you have e to the negative 4 pi k. And there is no way to relate this with your hyperbolic functions, because the arguments are the exponent has to be the same. So that is why it is not clear on how to proceed from here. And also, even if you try to maybe represent this as a series, that means you're going to go back to where you began with. So obviously we can't do that. So what we're going to do is that we're going to add and subtract 1 from the top. So we're going to write this as, let's get a little space in here. So we're going to write this as the sum as k runs from 1 to infinity of 1 over k to the 7th power, first of all. And then on this side, you have to write 1 minus e to the negative 2 pi, trying to see what is the best way to write this as. Okay, let me just write it as let me just write this way. It's not easy to simplify this. It may look simple, but not really. So you have to write 1 plus e to the negative 2 pi k. Then you have minus 1, all divided by 1 minus e to the negative 2 pi k. So in this case now, you will write this as the sum as k runs from 1 up until infinity of 1 over k to the 7th power. Then on this side here, I think we could notice something here, that we could write this as 1 e to the negative 2 pi k minus 1, all divided by 1 minus e to the negative 2 pi k. And then on this side you have a plus. So you have a plus 1 over 1 minus e to the negative 2 pi k. So we can simplify it in this way. So in this case, you will be having to deal with the sum as k runs from 1 up until infinity of 1 over k to the 7th power. And on this side here, this will be negative 1. I believe so, yeah. This is negative 1, alright? And on this side, you have a plus. On this expression here is related to cotangent. It's related to cotangent because if you recall from your hyperbolic functions, cotangent, the inverse cotangent of x is going to be for cos divided by sine. And for cos, you get e to the x minus e to the plus e to the negative x. While for sine, you get e to the x minus e to the negative x. So if you multiply top and bottom, by, say, e to the negative x, so you would have 1 plus e to the negative x. Yes, you have 1 plus e to the negative 2x here. You have 1 plus e to the negative 2x over here, all divided by 1 minus e to the negative 2x here. So basically, what you can do from here now, you can write at the very top here, you can add and subtract this. So you would have 1 minus e to the negative 2x plus 2e to the negative 2x, all divided by So we're making some progress. All divided by 1 minus e to the negative 2x. So if you do this, you get a 1 plus twice e to the negative 2x, all divided by 1 minus e to the negative 2x. So essentially, what this means is that, let's go here. What this means for us is a good news, because now we can write this e to the negative 2x all divided by 1 minus e to the negative 2x as to equal hyperbolic cotangent of x minus 1 all divided by 2. So essentially, this is going to be 1 over 2 cotangent, hyperbolic cotangent of x minus 1 over 2 as well. Yeah, minus 1 over 2. So what we do now is that everything here, even, we don't even need to go through all this pain, but everything on this part here is equal to, so we could just erase everything here we are done doing here. So everything here is equals to the sum as k runs from 1 to infinity of 1 divided by k to the 7th power. Then you have 1 over 2 times cotangent of, so it's going to be pi x minus 1 over 2. Yes, let me be sure, because it's going to be pi, so there's extra pi. Okay, it's not even s, it's going to be pi k or k pi. So it's going to be pi k, or let me just say k pi. Yeah, so when all is said and done, this would become the sum as k runs from 1 up until infinity of, so you have a half outside here, so you have hyperbolic cotangent of k pi all divided by k to the 7th power minus half times the sum as k runs from 1 up until infinity of 1 over k to the 7th power, and that would be half of, let's call it s of 1 minus 1 over 2 zeta of 7, because this is how we define the polylogarithms, as we say that the polylogarithms of order n evaluated at 1 is going to be zeta of n. We already discussed this. So I think if you look back at the answer to this, we already found one of them, so which is half of zeta of 7. Of course, that means this sum is going to equal all of that, the remaining parts. So let's evaluate these remaining parts here now. So here is the sum to evaluate. We are looking to evaluate the sum as k runs from 1 up until infinity of hyperbolic cotangent of k pi all divided by k to the 7th power. And to do that, we are going to recall the Mittag-Leffler expansion of cotangent of k pi. And before I made this video, I was solving this problem. I was like, okay, I have not really made a video on these expansions, but I'm going to quote the results here. But in the next probably few hours or so, I'm going to record a video featuring all this. So the result is that this cotangent, a public cotangent of k pi, is equal to 1 over k pi plus 2k all divided by pi times the sum as n runs from 1 up until infinity of 1 divided by k squared plus n squared. So this is how you get the expansion. Now this is not too hard to prove. It's very simple, not so hard. But we're not going to be supplying the proof here, because that would make this video too long. It's already 14 minutes. So let's see if we can avoid the temptation of trying to prove everything. So we're going to use that and invoke this sum into here. So you get the sum as k runs from 1 up until infinity of 1 over k to the 7th power. Then you have to worry about 1 over k pi plus 2k over pi times the sum as n runs from 1 to infinity of 1 over k squared plus n squared. And so let's proceed. So the first one, you pull out the pi, you have 1 over pi times the sum as k runs from 1 up until infinity of 1 over k to the 8th power. Then you have plus, so you have twice 2 over pi times the sum as k runs from 1 to infinity of what? So you have one of the k's here cancel out, so you have a 1 over k to the 6th power times the sum as k runs from 1 to infinity of 1 over k squared plus n squared. So from a sum, we went to a double sum, and now we are back to another double sum. For this one, this is just 1 over pi times zeta of 8. That one is clear. Then for this case, you have 2 over pi times the double sum as k runs from 1 to infinity, and then this as n runs from 1 to infinity of what? 1 over k to the 6 k squared plus n squared. Now we have this one is left now for us. This one is clear. The value is not too hard. You can look it up. For even power, zeta of, like for example, zeta of 2 is pi squared over 6. Zeta of 4 is pi to the 4 over 90. And then there is also zeta of 6 value, there's zeta of 8 value. So these zetas for the even part, this is going to be pi to the 8th power divided by something. So of course you can see that one of the pi cancel out, so you have a pi to the 7, which is what is featured on the problem. So we're not going to worry about this sum. We're going to come and write down this double sum to worry about now. Yes. After which we can compile the result, or I may leave it to the reader to compile the result. So you have a k equals to 1 to infinity times the sum as n runs from 1 to infinity of 1 over k to the 6th power, or you have a k squared plus n squared. Now, how do we deal with this double sum? It's very simple, nothing to it, because usually when you have a double sum featuring two denominators, one technique to use is you need to exploit symmetry. Exploit symmetry means that you need to recognize the fact that if you interchange the rows of k and n, the sum will be the same. It will not change. For example, this sum is technically the same as the sum as n runs from 1 to infinity times the sum as k runs from 1 to infinity of 1 over n to the 6th power. So you have k squared plus n squared. So this sum and this sum are technically the same thing due to symmetry. The rows of n and k interchange does not affect the final sum because a double sum. It may not be true that 1 over k to the 6 n squared plus k squared will be the same thing if the rows of k and n are interchanged, of course, because let's say we take k to be 2 and n to be, let's say, 4. So you have 1 over 2 to the 6th power, so you have 2 to the 2nd power plus 4 to the 2nd power. It will not be the same as 1 over 4 to the 6th power, 2 to the 6th power plus. But this time around, we're dealing with the sum. Okay, at some point k and n are equal to each other, so it's a sum, not really that is an expression, it's a sum. So we are summing all the various values of k and, because at some point, even though it is true that they are not the same, at some point, since k runs from 1 to infinity, at some point k of course will equal to n. At some point it will be less, at some point it will be more. So therefore this sum and this sum, we claim that the same thing. So basically this, we can take this off, and claim that this our double sum over here is actually equal to half of the sum, first of all, you get this double sum as k runs from 1 to infinity and as n runs from 1 to infinity, and then you have a 1 divided by k to the 6 k squared plus n squared plus the sum as n runs from 1 to infinity and then k runs from 1 to infinity, all divided by n to the 6th power. So you have k squared plus n squared. So we took the average because the two sum are the same, so they are the same thing. We took the average, and so we get a half, and then you get the double sum as k runs from 1 to infinity, n runs from 1 to infinity. Then you have a 1 over k to the 6. They have an n squared plus k squared plus 1 over n to the 6. So you have a k squared plus n squared. Now, again, you have a half times the sum as k runs from 1 to infinity and as n runs from 1 to infinity. So here now, observe that if we combine them, you will have a k to the 6th power plus n to the 6th power, all divided by k to the 6th, n to the 6th. You have an k squared plus n squared. And then, so this will give you a half times the sum as k runs from 1 to infinity, n runs from 1 to infinity. On this part here now, you can notice that a squared to the 3rd power plus b squared to the 3rd power is a squared plus b squared, and then you have an a to the 4th minus a squared b squared plus b to the 4th. So you have to write this as k squared plus n squared. So you have a k to the 4th minus n squared k squared plus n to the 4th, all divided by n to the 6th k to the 6th times n squared plus k squared. So this, of course, gets to be cancelled out, and you have to deal with half of n runs from 1 to infinity and k runs from 1 to infinity of what? On the first part here, you have a 1 divided by n squared k to the 6th minus 1 divided by 1 divided by n to the 4th k to the 4th plus 1 divided by, so you have an n squared k to the k squared. Okay, this should be n, this should be k squared, but you just write it as k squared n to the 6th this time around. Let's write it this way. So that means this, each of these sum now, we could write them as this. We could write this as half. So first of all, in this first case, you have the sum, the double sum as n runs from 1 to infinity, k runs from 1 to infinity of 1 over n squared k to the 6th minus half times the double sum as n runs from 1 to infinity, k runs from 1 to infinity of 1 over n to the 4th k to the 4th, and then plus half times the double sum as n runs from 1 to infinity, k runs from 1 to infinity of 1 over k squared n to the 6th power. So these two sum, of course, are one and the same thing, only a matter of changing. So we could write them as the double sum as n runs from 1 to infinity of 1 over n squared times the sum as k runs from 1 to infinity of 1 over k to the 6th power minus half of what? The sum as n runs from 1 to infinity of 1 over n to the 4th times the sum as k runs from 1 to infinity of 1 over k to the 4th. Again, we already have defined all of these sums earlier on. This is equals to zeta of 2 and this is equals to zeta of 6, and this right here is half of, this is zeta of 4, and this is also equals to zeta of 4. So essentially now you have to the pi squared over 6. What is zeta of 6? Okay, you can find the value of zeta of 6 is pi to the 6 over something at the bottom here minus half of zeta of 4, I think pi to the 4 of 90, so minus half of pi to the 4 over 90 times pi to the 4 over 90. So you have a pi to the 8th power, that's 90 times 90 is going to be something. So you notice that this one is going to be pi to the 8th power divided by a denominator and minus pi to the 8th power divided by a denominator. But observe that the problem statement featured pi to the 7. So which means that, okay, there's a 1 over pi here. Let's go up and see it ourselves. So this 1 over pi here actually helps us in cancelling out that denominator in that pi. So we will end up with pi to the 7. If you collate the terms together, you would have that this our double sum over here precisely is equal to what we claim it is, 19 pi to the 7, because we had a pi to the 8, but it's a 1 over pi. Then you have a minus 1 over 2 zeta of 7. So everything checks out and we have been able to evaluate this sum. So thank you very much. Thank you so much for watching this video. Please do subscribe to the channel. Bye, and do have a lovely day. Have a nice day. Bye.